In simple terms, our universe can be compared to a balloon. Until the early 20th century, many scientists believed that the universe had always existed and was unchangeable, as if the balloon had always been inflated. However, when Einstein first worked on his theory of relativity, he found out that the gravitational forces meant the universe was actually collapsing. The balloon was contracting.
The problem Einstein had in 1917 when he tried to solve cosmology was the following. It showed that the universe should be in motion. And so he invented something, the cosmological constant. And this was a term which could offset matter in the universe, and Einstein thought stabilize the universe against collapse or expansion. Turns out it doesn't work mathematically. The equations still remain unstable, and so it was a mistake.
Shortly after, the Russian scientist Alexander Friedmann tried to solve Einstein's field equations. In 1925, he demonstrated how the universe stays stable without any cosmological constant, only if it keeps expanding. Independently of Friedmann, the Belgian Georges Lemaitre worked on the equation as well. With the help of older observations, he found the first indications that distant objects are moving away from our galaxy. Therefore, expansion would have to be the right solution. However, according to Lemaitre, if the universe was expanding, it must have had an origin. The balloon, therefore, must have been empty once. In 1929, Edwin Hubble discovered that the further away galaxies are, the more the wavelengths of the spectrum shift towards red. Hubble not only confirmed the expansion of the universe, but also Lemaitre's discovery that the universe had an origin. Later, this observation was to be called the Big Bang theory.
And so you're going to have, if you look back in time, a time when the universe is both very hot and dense. And hot and dense is like the center of the sun. It's a nuclear reactor. So one of the first things we could do with this model is go through and predict how much stuff should have been synthesized in the early universe.
The development of the universe is divided into several time periods. It all started with the inflationary phase. While cooling down and still expanding after the explosion, the universe filled up evenly with an enormous amount of hot energy. When it further expanded and cooled down, elementary particles and forces crystallized out of the hot energy sea. Then nuclear particles crystallized out of the elementary particles, particularly neutrons and protons. Much later, the universe had expanded and cooled down enough for its temperature to have decreased from nearly infinitely high to just below the temperature of our Sun. When protons and bigger nuclides caught the electrons, they formed the first atoms. At this time, the universe became transparent, and photons could travel across the universe. This is the earliest stage of the universe that we are able to observe through our telescopes. It can be seen as a hot plasma surface being so far away that the light is red-shifted into a microwave spectrum. By measuring a constant, namely fossil radiation in the sky, Arno Penzias and Robert Wilson discovered the cosmic microwave background, CMB.
Look at the cosmic microwave background back when the universe was 1,100 times smaller, then you're looking back about 13.7 billion years. And that's about as far as you can see, because the beginning in time is beyond that, but it's shrouded the same way the center of the sun is shrouded from us by the plasma of the sun, so that we only see the surface of the sun. And we only see inside the sun by using sound waves that make it to the surface of the sun. Likewise, we only see earlier in the Big Bang by using sound waves that come from early in the Big Bang and make it to the surface of last scattering, the photosphere of the sun, and then we can sort of interpret that the same way you get an ultrasound and you turn that into a visual picture you can use.
For their proof of the CMB, the two Americans received the Nobel Prize for Physics in 1978. John Mather and George Smoot, both astrophysicists, later worked on a satellite at NASA that was able to visualize this so-called black body radiation. The result, the Cosmic Background Explorer COBE, examined the CMB to cast a new light on the past of space. It provided evidence for small anisotropies that had developed on the CMB due to temperature fluctuations.
17 years after that, we got a call from Stockholm. because we had measured the Big Bang spectrum, and it was indeed virtually perfect spectrum. We also measured the map of the radiation, and we found out it has hot and cold spots. There are now more scientific papers written about those hot and cold spots than there are spots on that original map.
After becoming transparent, there was a period where the universe was filled by a cold gas and no star had yet formed. This time is therefore called the Dark Age of the universe. To form the huge cosmological structures like galaxies and galaxy clusters, the still rather isotropic cold gas had to agglomerate. The most important component for the development of these structures is dark matter. Usual matter can be seen as bright stars and galaxies, or when reflecting their light. Dark matter is completely transparent to light, so looking at a region full of dark matter will appear dark. Dark matter is almost 5 times more abundant than usual matter. The stars, galaxies, and galaxy clusters all swim within an invisible gravitational sea of dark matter.
Turns out we also had this issue that trying to make galaxies form, we couldn't do it just with atoms. We needed something else. And we call that cold dark matter or dark matter. We need this stuff not to interact with atoms. It really needs to only interact by the weak force to make it work. It gives the structure formation of the universe via gravity, and it's consistent with the idea that when we look at galaxies, we don't see material to explain the gravity we see out at large, large distances.
The outcome of the Millennium simulation in 2005 confirms that the cosmic structures of galaxy clusters developed with the aid of dark matter from the initial fluctuations found in the CMB. 5 billion years from now, the universe will enter its last phase. In 1988, the 3 scientists, Saul Perlmutter, Brian Schmidt, and Adam Rees, discovered an accelerating expansion of the universe and shook the very foundations of cosmology. In 2011, their work was rewarded with a Nobel Prize in Physics.
We would like, and this is a top priority for both Europe and the United States, to continue to measure better the acceleration process. We know pretty well what the acceleration is nearby. We would like to know the history of the acceleration. Now, as you go farther back in time, the acceleration is smaller relative to the expansion rate that already occurs. So it's only in the last 5 billion years that acceleration has been dominant. Nevertheless, we would like to know the entire history of the acceleration, because then we would be able to say whether that W, that parameter that he showed in his equations, is actually a constant. No one can prove that it's a constant. We are right now assuming that it's a constant.
The acceleration can be explained by a mysterious dark energy, which makes up more than 70% of the total amount of energy in the universe. Ironically, Einstein's cosmological constant is also able to explain this phenomenon. Although both dark matter and dark energy remain a mystery, one thing is for sure: they'll have great influence on our future understanding of the universe.